Good afternoon, everyone. My name is Pete Sauer, and I'm happy to welcome you to the TCIPG monthly seminar from beautiful Urbana, Illinois.
It is beautiful today.
It is beautiful today. The boyhood hometown of Roger Ebert, for those of you that know him and knew him, who somewhat prematurely died yesterday, but we continue to recognize him as a hometown favorite. We're getting ready for a summer school, which will be held actually near Chicago in St. Charles, Illinois, the week of June 17th, Monday through Friday. If you go to our website, TCIPG, and you won't be able to miss it, the Sunday school, or the summer school, please go and check it out, see what's being presented, and if you can, join us for that week. It should be very interesting and educational. And it's near O'Hare Airport for travel purposes. It's actually St. Charles, Illinois. Today I want to introduce our speaker from outside, all the way from the great state of Philadelphia. Doug McGinnis has been with Exelon Corporation for something over 30 years and started out in nuclear engineering and somehow migrated to the IT group, the information technology, and is now a principal network architect both for the smart grid and other Exelon resources. If you're not familiar with Exelon, it is the parent company of three major utilities: Commonwealth Edison, serving the city of Chicago; Philadelphia Electric, serving the city of Philadelphia; and Baltimore Gas and Electric, serving the city of Baltimore. So it's a huge territory, and it also has a generation component. A lot of the nuclear reactors in the country are managed by Exelon Nuclear, so Doug is familiar with the generation side and the transmission distribution business, and especially communications. So he has advanced degrees, a master's degree, I believe, from Penn State in nuclear engineering, and is here today to talk to us about smart grid communications architecture, for which he's involved in lots of activities and work. So, Doug?
Thank you, Pete, and Bill, thank you. I want to thank everyone for the hospitality you've shown me over the past 2 days, and it's been absolutely fabulous seeing the research that you're engaged with and enlightening. So I appreciate the efforts that you're doing that will someday make our lives a little bit better and a little bit more secure. So from that standpoint, I do give you kudos for those efforts. So what I'm here to talk to you today about, and I'll start out by saying that these are my express opinions, not necessarily the opinion of Exelon. So, and I'm very opinionated, I've been told, but nonetheless, what I'm going to share it's going to be a lot of philosophy. It's going to be some high-level discussions. Then we're going to go into the deep details of the communications technologies. So those beanie heads out there that like to have their propeller spinning, we'll get down into that as deep a level as you want to there, and then talk about where we're headed in the future. So I've been involved in the smart grid since for about 5 years. Okay, so back around 1997, 98, got into this arena in communications. So we'll talk a little bit more about that, but. I see what we're doing today, as a deployment of smart grid generation 1. Okay, so what we're building out is kind of like the first evolution of the smart grid. Grid automation has been around for a long time, so this is not like all new stuff. There's been a lot of SCADA devices out there, and substation and automated devices. So this is really just taking the smart grid, is really just the embodiment of that into a converged framework, is the way I like to refer to it. it's being also supported by evolution of standards. You know, a couple months ago, we had George Arnold here talking about the Smart Grid Interoperability Panel and the efforts that they're trying to do to build open standards, modeling for the technologies and deployment of the smart grid. So the unfortunate thing is a lot of us are working in parallel with that to try and deploy a smart grid into the environment before all those standards get ratified. So again, that's one of the reasons I think we're kind of in a Gen 1 of smart grid deployment, but there's a lot more to come along those lines. I also see, and I heard it yesterday, about application requirements. I mean, the work that you guys are doing and the work that the business wants to see happen on the grid is just going to be more and more data. The data appetite out there is just going to ever grow, driving us to get more technology out into the field, get more sensor data at higher interval rates and polling rates, and it's just going to want to consume a lot of bandwidth. My personal opinion is that I don't think that the technology we have out there today, especially far into the field, are going to service that requirement for added bandwidth in the long haul. Now that's not in the near term, but this evolution is just going to continue to drive the need for bandwidth. And the RF technologies are probably not as mature as they need to be to support that. So we're in the process of migrating from a legacy analog environment to an IP-centric communications infrastructure. That poses all kinds of issues, both in the security front as well as support. The old legacy infrastructure was fairly easy to support, not necessarily super reliable, but fairly easy to support. But now we're going into this IP-centric environment. It's a whole different model, and of course moving towards open standards. So the journey that we embarked on, again, I said we started out around 2007. ComEd did an AMI pilot in 2008 and 2009. PECO got a $200 million grant award from the stimulus fund, the ARRA fund. We built out 360 miles of fiber, deployed a census AMI solution, and from that we built the whole strategic framework around a multi-service network architecture. Today we have in PECO we've completed that work. I mean, for the most part, there's still a lot more deployment of metering, but the network piece is by and large installed and running per the design. So, how did we get there? We started out with a strategy. I mean, the strategy is embarking on anything of this nature, you need to start out with a strategy. What are the business requirements? What's the problem you're trying to solve? How many, how fast, all that sort of thing. You need to define a clear strategy with a clear vision of what it is you're trying to build, establish some fundamental design principles, which we're going to talk about, and then define an architectural framework from that. And then move into the standards, define what kind of design standards you're going to apply, and then identify the technologies that are going to meet. So this is a mapping operation. Each one of these things maps up to the other, and that way you stay consistent, you stay aligned, and you build what you set out to build to ultimately meet back those business requirements, and then you execute or just do it. So some of those design principles that we started out with. Security, is number one. Right? So if anybody from a utility gets in front of you at any point and says that security is not important, then clearly their priorities are misguided, and really they're off the mark, and opening themselves up for trouble down the road. Certainly with all the press around cybersecurity and vulnerabilities of the grid. Are key aspects of what we have to be mindful of moving forward. So I've always put that at the top of the list, and we actually got pretty good engagement from the executive team in supporting that approach. Converged communications. We're going to have a converged communication infrastructure, but with maintaining logical separation. I'm going to talk more about that later. Interoperability. Moving toward those open standards. A lot of the technology out there right now just is not really open. Even some of the claims to be open, we found are not necessarily the case. We got to get to the point where a smart grid device, or where I'd like to see us get to the point where a smart grid device is kind of like your Wi-Fi and your laptop, where you can have any brand laptop associated with any brand access point and things work. That's not where it is today.
One quick question to get some context. As I read your bio, it sounds like you're the owner of this.
Yes, okay. Now you put me on the spot here. I led the team that put this together. This was formed with a lot of people in the room. Okay, so we had people from the business, we had people from IT, we had people from the utility, as well as many vendors. So it wasn't all my idea. So I was just the one that kind of collected things and pulled it all together.
Right, so you're, in a sense, you're the champion that made it happen. There are always lots of other players.
I'll take credit for that, yeah.
Okay, good, because that helps us understand the standpoint from where you're talking.
I was the architect. So, but like I say, there was a lot of people that played a role in this, and that I think was key to the success, because we had the buy-in from the business in terms of what it is they wanted to see get built, as well as from IT to be able to deliver on that solution. So, but anyway, okay. So back to the presentation. Privately owned communications. This is a philosophical discussion, and a lot of people would be on the fence to say, well, why don't you go with a public carrier versus a private? We picked private as the direction we wanted to go, namely because we just don't feel that the public carriers have the ability to meet the SLA requirements, the performance and reliability requirements long term. So again, that's not necessarily true for everyone. Not everyone feels that way, but I think there is a large standing in the industry that would agree with this. Also, it doesn't mean everything has to be private. I mean, there are going to be cases where you're in a remote location where you just can't get your technology out there, or it's going to be prohibitively expensive. You got to do some business case modeling of that, right? So you have to really look to see what is the best approach. And then no unanalyzed single points of failure. So these are really the founding principles for which we built our technology. That led us into a multi-service communications architecture. We talked about being converged, looking at the business applications, multiple applications going into the substation, not just telemetry, right? It's not just RTU telemetry coming out of the substation now. We got video surveillance cameras. We got other security systems. We'd like to have access to the enterprise network there. So there's a lot of different services at AMI, distribution automation, numerous services, and more to come. So it's got to be flexible. So in convergence and alignment, again, looking for to share a common transport. We can't build separate individual networks for each one of these application services in a cost-effective way. And so again, that leads us to a multi-service architecture. Security. So I'm not even going to try to teach anybody in this room about security, but obviously a defense in depth approach is the mantra. And looking at the various vulnerabilities and doing risk assessment. It's all about doing risk assessment. What's your risk tolerance in securing this environment? What can you live with versus what are you willing to accept as a consequence? We're looking at deploying obviously firewalls, IDS, intrusion detection systems, and making sure that we have enough barriers out there to protect the environment. And I think we've done a pretty good job, but I think from what I hear from the work that you guys are doing, there's a lot more that can be done. And so I'm looking forward to seeing some of that come into commercial availability and viability. Defense in depth, again, looking at it from a confidentiality, integrity, and availability standpoint, the CIA triad. Every technology selection we make, or every architectural selection we make, we evaluate that against, are we maintaining those three fundamental tenets, and if not, why not, and what is our exposure at doing that? Again, using firewalls and encryption authentication throughout the network end to end is, seems to be the reasonable answer, but how that gets implemented and defined are challenging, and the technologies are not necessarily as robust as we would like to see them in that area. Okay, so what does that look like? So this is kind of a party starter, I think. You know, if you're out in the, with your girlfriend or boyfriend and things get boring, you whip this out and you can discuss the end-to-end smart grid infrastructure. So, and I'm not going to spend a lot of time going over this, but it gives you some visibility to and line of sight to how complicated and how much infrastructure is involved in dealing with the smart grid. You got the HAN, the home area network, you know, where you have your thermostats and in-home devices. And the meter, going through this communications, uh-oh, did something wrong there. Okay, going through this communications environment and then into the head-end systems. And notice that we have these two separated out as AMI and distribution automation. When I say DA, I'm referring to distribution automation, which is grid devices, reclosers, capacitor bank controllers, and faulted circuit indicators, and those types of devices that are coming out of the substation. And then you got your head-end systems, and on the AMI side, your MDMS, meter data management system, which is going to have hordes of data coming into it. You know, so storage is going to just be explosive over time, depending on what kind of interval reads that your AMI system is designed to manage, and then on into to the billing system. Similarly, in the DA, and each one of these has to have its own security context. I mean, you have to have encryption and authentication and ensure that the integrity of that information is maintained, as well as the privacy. I mean, privacy is absolutely huge in where we're going in the long term, because the customer's got to have faith and trust in what it is that we're doing with their information. So again, it's an eye chart. If you're interested, in looking at the slides later, or I think you can download them and read through that if you have any questions. So multi-tier communication. Let's dive down into this a little bit deeper and start getting into some of the technologies and get the propeller spinning. So we have a 3-tier comms model here that we've defined. Personally, I'd like to see it get collapsed into 2 someday, and the next version of Smart Grid. But for right now, we have a 3-tier model. This is pretty classic. I mean, this isn't like some type of brainstorm. It's a pretty common sense model that we applied here. You got your tier 1, your high-speed backbone communications, which is based in fiber and SONET and point-to-point microwave technologies, and so it's on the order of a gigabit. And coming into this, I thought, man, we have a gigabit on the backbone. That'll take care of us for a long time. And I was sitting down with a gentleman this morning. He said, "Oh, we'd like to see about 10, 20 gigabits for the PMU data and that sort of thing." 10 or 20 gigabits. Oh my goodness, that's like a lot of data. So you're already tapping out our model, where I thought we would have plenty of capacity. I thought we'd be just fine with a gigabit in the core, but maybe not. So again, what the demands that are going to be made are going to challenge the bandwidth very quickly. So the tier 1 goes through the substations, and I got some more drawings here that'll help to clarify this. Tier 2 is what I call the medium speed backhaul or bridging network. Technologies are WiMAX, LTE, kind of the popular ones for right now, and they're pretty well developed, and they're pretty open standard. So I mean, those are very mature, or much more mature technologies, have a reasonable level of security built into them, and that sort of thing. I mean, security again has to be built into the whole overall fabric of the technology and the smart grid. I mean, that's really the way what it comes down to. And then tier 3 is that field area network, or where the AMI system sits or the DA system sits, a fairly low bandwidth on the order of a couple hundred kilobits per second. So we're going from a couple hundred kilobits to maybe tens of megabits per second in the tier 2 to gigabit and probably more in tier 1. What does that look like kind of in another cartoon? So again, you got a SONET ring where you got ring topology. An interface with the back-end SCADA bus or the head-end system, a tier 2, which is that WiMAX, And then a tier 3, which is really where the field units sit, the transformers, reclosers, meters, et cetera. And then really there's a tier 4, which is that home area network. I'm not going to talk too much about that, but that's more to come.
Hey, Doug?
Yes, sir.
This is really great. I mean, seeing this all laid out from a communications viewpoint. I wonder, and if it sort of takes you off track, you don't have to do it now, but as you're going along, in addition to, of course, security requirements and trust requirements, which we really are concerned about here, it's our impression that those requirements cannot be considered in isolation, but only together with performance requirements on latency times and all these different networks that you're talking about hooked together. And so I wondered what your impression of that was, and if, as you're sort of explaining the architecture to us, to what extent have you laid out performance requirements that you need to achieve while being secure?
Okay, that's a great question, and that we had a lot of dialogue around performance, especially as it relates to latency, as well as capacity. Because, as you're aware, anytime you overlay some security technologies, you usually take a hit on performance. And as such, we had to do a lot of lab testing to validate what those latency requirements or latency tolerance is. I would say that in some cases, it actually got worse than what it is today with the the existing analog system. There's multiple second delays going from head end out to the field and back again.
Are there numbers that perhaps offline you could share with us about, from an application point of view, what sort of performance you need to achieve, and that would help us?
I do have some numbers I could probably get to you. I mean, at a high level, what the tolerance level for in SCADA space is about 5 seconds from an operator activating a device to getting confirmation that whatever action actually took place, and that's kind of at the high level, the extreme. Obviously, faster is better. The more technology tiers you get in here, the more hops you get in, obviously the worse the latency is going to be. So that's why I think further collapsing of the tiered architecture is going to be necessary in future generations of smart grid communications to reduce that latency. But by and large, we just have to accept what's available to us right now. The options are fairly limited. Talk a little bit about a substation LAN, where the communications gear go into the substation. We're installing Alcatel-Lucent routing infrastructure that supports an MPLS, multi-protocol label switching, which is a technology supporting application segregation. We don't allow any inter-service or inter-substation routing. So they're really configured as point-to-point circuits, even though they're operating over ring topology. And that's just to ensure that, to further enforce that security barrier. Access is, so if you access an RTU at a substation and you're sitting in the substation, you get on the enterprise network, go back to the core, and then re-authenticate back out through a firewall. To get to that RTU or relay device that you're configuring, again, from a security perspective. The WAN architecture is going to be, again, layer 3 with MPLS. We've defined seven application tunnels or application groups. RTU telemetry is going to be encrypted. Not all the other groups will be encrypted though, but it's flexible. IP addressing schema is well defined for the entire substation population up front. Talk a little bit about relay protection, teleprotection. That's the communications between two relays. That, to me, and to us collectively, is kind of like the holy grail application for the substation and for the utility in general, because that ensures that the relays or that any kind of fault in the transmission system or distribution system can be cleared before bad things happen back in the substation. Like if you fault one of the high transmission lines, you could blow up the transformer that's sitting in the substation, which would be a real bad day. So you need to have these communications very reliable, very robust to be able to clear the fault. So a lot of what we did in building out that tier 1 core network was really driven by the need to have that reliable relay protection communication. So that's something that, you want to, I really like to drive home the importance of doing that. In fact, it's so important that we built 2 rings. So I showed a single sonnet ring, but in actuality what we did in PECO was build 2 rings in parallel to one another to have a primary relay ring and a backup relay ring. So that just gives you a feel for how much we're willing to invest in ensuring that communication stays reliable. So that's all I'm going to say about it. It's 2 dual counter-rotating sonnet rings.
So I have a question with respect to microgrids. When you start to have owners that currently want to generate energy but also use it, how does then your substation communication architecture manifest in these microgrids, or when a city or a smaller town wants to? Europe actually has very much these microgrids, and I always have these discussions. How would this communication architecture look like?
Yeah, well, that's a problem that's coming. Okay, we have it with people with solar cells on their houses and that sort of thing. And that's not too bothersome. But there's going to be a day when, as you say, you're going to have smaller generators that are generating enough capacity to drive the power on the feeder. Because the grid is designed to work as a one-way street. Right? Power coming from the generator out through the transmission system, down to the distribution system. It's not intended to drive power from the distribution system back up through the transmission system. That's not going to work. So, from a communications perspective, we're probably going to have some kind of monitor. We're definitely going to have some monitoring on what it is they're doing, and be able to have a level of control on it in order not to saturate a feeder and create an overvoltage condition in that area. So, and that's something that you guys ought to start thinking about, and tell us what the answer is. So I don't know that I have a really good answer for that, but it's a problem that we recognize that we have to deal with, and again, any assistance we can get would be greatly appreciated.
My days with the electric cooperatives, met that 15 years ago, and when I was with electric cooperatives 15 plus years ago, we were dealing with primarily wind at the same time, and part of the interconnect agreement it was written into it back then that if they were going to have a generator, we had the whole work set up so that, disconnects and everything, because not only do you have the problem of generating, backing up the line, but when there's an outage, it's very dangerous to have that machine there generating and feeding what you think is a dead feeder.
Right, and that's a problem even in the home situation. You have a dead feeder, and the linemen are out working on it, and you got a home generator that's generating, and all of a sudden it starts putting power back onto the feeder, create a hazard for the linemen. Okay, so I'm going to quickly go over the 7 application groups that we've defined. You can add more as time goes on. It's a very easy process within the MPLS environment. Telemetry, just straight RTU telemetry. NERC SIP telemetry, we felt that was a different security level, and that would be for CCA or critical cyber assets that are defined under the SIP standards. Distribution automation telemetry, enterprise access for business apps, security, AMI Tier 2 backhaul, and a management framework. Video is going to be the big driver in terms of bandwidth, and I guess until the PMU's phaser measurement units get kicking some big data rates. Yep. Surveillance video and substation is going to be very key. It's probably be part of the SIP standard too. I mean, I'm not sure on that, but it probably will be to have some kind of surveillance video. And just to kind of put it in perspective in terms of that gigabit pipe, what those tunnels look like in this cartoon. Again, another perspective of that logical architecture. I got a couple drawings in here just to show it in a different line. The top there represents the substation and how those application groups are set up. hitting a substation router, a single substation router, dual power supplies, but that substation router is a single point of failure for that substation. But we've analyzed that from the standpoint that we are willing to accept the risk that that thing goes down, that we lose, we know what the boundary of what it is we're going to lose visibility to. And then we have two head-end handoffs that are redundant. Again, we got a ring architecture configured as a point-to-point solution with a primary and backup location. In PECO, I mentioned we had about 360 miles of fiber built. These are the 6 rings, the 6 sonnet rings that we built as a part of that, and they're co-tended together, and they go back to to 2 data centers, one at our main office building in Philly and one up in Plymouth Meeting, and then all the other infrastructure laid out behind that. Again, I'm not going to spend a lot of time, but it's an interesting diagram, again, if nothing else, to illustrate the complexity of what it is that we wound up building. With, of course, a firewall that comes out of the router. This is really the entry point, this firewall here. These 2 firewalls are really the entry point where the IDS is located, the intrusion detection system is located to manage or monitor what's happening on the smart grid. But we don't have IDS all the way out in the field. And I know some of the research you're doing is to look at putting IDS on more discrete devices out in the field, which I think would be a real asset, because again, there's only so much you can do when you're monitoring from the front door, because there's a lot of other back doors out there. We also did something interesting in WiMAX deployment, and we did this actually in ComEd, and I just wanted to share quickly. We actually built a system that would be totally redundant in WiMAX space. So we actually have a substation that points to 2 base stations through two different CPEs or subscriber radios, 2 subscriber radios, each one pointed at a different substation, and then using the MPLS to manage the failover. So it has a primary path back through across the WiMAX, and the MPLS is actually running over the WiMAX, and then it goes to its respective head end. If you lose that link, it'll do an auto failover to the backup base station and maintain continuity or connectivity throughout the system. It actually works pretty well, although we have one link that's in ComEd that's creating some problems, but not because of the technology, just the fact that they mounted it underneath the transmission tower, that the EMF from the transmission tower seems to interfere with the RF from the WiMAX. So interesting dilemma. All right, so and then inside the substation, again, we have a tier 1 bridge to the tier 2 for AMI back and distribution automation. We can also put a substation on the WiMAX. So you can actually have the substation being a client to a WiMAX base station and carrying all these services across that WiMAX infrastructure. Support QoS tagging. And in WiMAX space, what we picked was a 3650 or 3.65 gigahertz spectrum WiMAX solution. Gets good 3 to 5 miles and up to 10 miles with some loss of performance, obviously, the further out you go. And all this is about converting the substation to an IP environment, right? So we're doing IP in the substation where you have a lot of the legacy protocols. A key piece here is you need to have these services support the future of where we're going and also be able to support the legacy, okay? So we have a lot of legacy comms technology out there, serial, bit-oriented protocols that are very cryptic and they're not, and the RTUs are not going to be replaced anytime soon. It's just too expensive and too big of an effort to replace the RTU. So we're going to wind up the IP technology has to be able to deal with that and be able to transport it in an effective manner, and it does. And you can do TDM emulation, for instance, over MPLS or over IP, and it works pretty effectively. And get rid of the old analog circuits. Verizon and AT&T, they don't want to. They want us to get off of them. I mean, they want to retire it and sunset it as soon as in the next few years. So what's next? Smart grid generation 2. So this is where I think the convergence of those tiers out in the field that tier 2 and tier 3 need to occur. We really need to have the ability to develop and deploy a broadband RF solution that's going to meet the needs and the performance needs that Bill mentioned in terms of being able to have faster data rates out in the wild. Keep in mind, like the current mesh technologies that we have out there. So, a lot of what you're working on here in Itron space is a mesh technology, and what we're deploying in ComEd is a mesh technology, a Silver Springs mesh technology. That's going to have inherent latency on a hop-by-hop count. Every hop is going to add, an incremental amount, I think on the order of like 20 milliseconds of latency per hop, through the network. So the more hops you have, the more latency you have, and the less performance you have. So if you can get that converged down into a single network environment that has adequate capacity. So what's to stop us from doing that? So when I look at the business analytics that are coming in, again, the evolving business requirements and security requirements for that matter, the application data appetites, is ever increasing and resulting in an ever increasing network utilization. My opinion, narrowband and the unlicensed spectrum is not going to sustain that for the next generation applications. Now, I understand you can put more access points out there to increase the density of the mesh, but I think ultimately you're going to exceed the capacity that is possible by these mesh and unlicensed technologies. So in that generation 2, what are we going to have to do? We're going to have to increase the bandwidth, evolve the RF technologies, and it comes down to spectrum. I mean, everything we've seen here in RF space, it's about the spectrum. Spectrum is really the transport mechanism. You can think of it in it's like the fiber or the copper or whatever. It's really the more of it you have, the more data you can transport over this infrastructure, and that's been our Achilles heel in trying to deploy more of this broadband or higher speed infrastructure out there. So spectrum is critical. I think we need about 10 to 20 megahertz of spectrum. Obviously, more is better, but I think it's a good starting point. We're actually looking at this in a study I'm working with UTC to look at how much spectrum do we really need. I don't think anybody's ever came out and said you need X number of megabits per second throughput on the grid to support everything you need. And of course, there's a lot of variability in there depending on what it is you're trying to do. But what we're trying to do is formulate a study to look at that requirement to get a baseline of what bandwidth consumption is going to be required for these various applications that we can, as an industry, to the extent possible, agree upon. Getting utilities to agree upon anything is like herding cats. But spectrum is not readily available to utilities, or we have to buy it. And we have to buy it and compete against the telecom companies, the Verizons, the AT&Ts, and Sprints of the world. And that's very very challenging for us. It can be cost upwards of $20–30 million for that type of 10 or 20 megahertz of spectrum for our territory. So it's a very expensive proposition. There might be other avenues like creative alignments with the public safety on their 700 megahertz that they just got allocated 20 megahertz of 700 megahertz spectrum, and there's possibility of some sharing arrangements, but that's not even nirvana either. So what we're trying to do is try to find some ways to get access to some broadband spectrum, and then you can build the grid end to end under one technology. Again, my view, not necessarily the views of Exelon. Yes, sir.
I wondered if television white space, which has been under consideration, would provide any help here, because that's useful particularly in rural areas.
Yeah, it could be. The television white space might be some availability out there for us, but again, we'll have to see how the auction proceedings go, because I think they want to, basically the DOE and NTIA and FCC want to auction the spectrum. Whatever spectrum's available, they want to auction it to the highest bidder to make money. We have a number of lobbying efforts with the FCC and NTIA to try to get some utility dedicated spectrum or accessibility to us. We haven't been successful in doing that. You know, even paying a nominal fee or something like that. But it's hard to try to convince our leadership, our executive leadership, hey, let's go out and spend $20 or $30 million on air, you know, on this thing called spectrum. It's a hard sell. And with that, I'm going to open it up to any questions.
So, Carl Reinhardt, University of Illinois. Several questions. The first is, you know, as I look at the Exelon website and they talk about conducting business in 47 states, but it sounds like from a utility perspective, there are really 3 large nodes of operation. So does your network extend all 47 states?
No. No. So a lot of that would be like sales, retail sales, and
Services.
and other generators and that sort of thing. So we do conduct a lot of business in other states, but we don't. Our network, outside of those 3 metro areas, we go down to Texas, we go up to Connecticut, and where else do we go? I think that's the dominant areas of where our enterprise network extends. Our SCADA real-time networks really are in those three regional areas: Philadelphia, Chicago, and Baltimore.
And when you showed your diagram, you really didn't indicate the differences in the different levels of the system in terms of distribution, transmission, or generation. But those reside in different companies. So does Exelon dictate network policy to its subsidiaries?
Yes. Is this the diagram we're referring to, or?
Well, I think there have really been several.
Okay. Well, let's let me try to dissect the question this way. First of all, most of what we're talking about here is on the distribution side. There are components, because we did run fiber through transmission substations, you know, and we're doing that in both the ComEd and PECO. So we are running communications into those substations. What we're doing in smart grid space, though, is predominantly on the distribution side, getting the DA devices out there into the distribution grid. Transmission side is more that relay protection, that teleprotection service I mentioned. So while the fiber is running through those substations and we're setting up the multiplexers and we're using Jungle Mux, the GE product for that service, that's going through the distribution subs.
And so your architecture is a combination of corporate-owned and leased, for instance, you're leasing lines from telecommunications companies.
Yes. Currently, we lease a lot of lines from telecommunications. In fact, and what you see right there in the 6 rings of PECO, we actually built another ring too. This drawing doesn't reflect it for 7, but where at all those substations where we have relay and protection going on, we're migrating public carrier circuits that were very poorly performing. You know, I shouldn't say the carrier, but we had, you know, frequent problems, downtime with them. And when one of those lines goes down, you have to swap to a backup, because again, the relaying is that critical that if you don't have that service, you got to take the line out of service, and taking the transmission line out of service is really not a good thing. So again, we for the teleprotection, we've migrated close to 400 or 500 circuits, I think. I might be wrong on this, but overall we're saving over $1 million a year already in doing that, what we've migrated thus far, and we're still migrating. So it's really had a cost savings. Now, is it going to pay for this? In 30 years it will, but you know, and once we get everything migrated over, we're going to be saving probably upwards of $1.5 million a year on public carrier circuits. So we're trying to get off of it. We're not there yet, and we never will all get everything off of it. I mean, because we just, again, our fundamental principle is use private, but if it doesn't make business sense, we're not going to do it. You know?
And so it sounds like you're building a unified communication structure that
Yes.
crosses Exelon and its subsidiaries.
Yes.
Okay.
Yes, and I will add that we're building the same architecture in both PECO and ComEd with the only differences would be those required to meet the business need, but fundamentally it's the same foundation in Philadelphia as it is in Chicago. That was bringing the two utilities together to agree on that was an exciting challenge as well.
I bet the challenges aren't finished.
Yeah, no, exactly.
Cultures are hard to change.
Hi, Gabe Weaver, UIUC. I had a few questions, but I'm going to start with the first one. Back on the communication design principles slide, you had a bullet, no unanalyzed single points of failure, self-healing. So I was wondering first, do you have any specific examples of that?
Yes, the substation.
Back where you're showing the green communication lines, or?
In the substation, we have a single router.
Okay.
So we decided. So one option, there it was. One option would have been to put two routers in, with two, and put it on the sonnet and such, because we do have two sonnet muxes in every substation for the inbound fiber and the outbound fiber, and we actually have four because we have two rings, and each one of those rings has two muxes. Yeah. So in that case, we have diversity and redundancy with the multiplexers. But the router, which is carrying the IP traffic, we made the decision to only go with one of them. Huh. So now the router has lots of redundancy built into it, but there is a failure mode that could take that router down completely, okay. Or stop the service. We made the decision that was an acceptable risk to live with. So the intent is not to have no unanalyzed single points of failure, but to make sure that you evaluate when you do have a single point of failure, that you accept the risk of a problem.
Okay. And I guess the other question is, so when you're looking at these kind of points of failure analyses, is it at the device level usually, like a router or a piece of hardware, or do you also consider at the software level as well potential for points of failure?
Well, yeah. I mean, it would be the device and everything upstream and downstream of that device that could be possibly impacted. But I mean, obviously the software locking up or something like that could be and it happens, right? I mean, routers do that. But yes, we do try to evaluate both at the software level. Now, it's not, don't give us a lot of credit in terms of doing like a detailed, spreadsheet analysis or risk-based analysis of it. I mean, it's more like a discussion kind of analysis, and say to the business, all right, this is what's going to happen if this thing fails. You're going to lose this capability, or this service is not going to be available to you until we get somebody out to fix it. And that might take 4 hours or 5 hours or 6 hours. Are you okay with that? Yeah. So the business is generally okay with losing visibility to a substation for a short period of time, several hours. What they get upset about is when they lose visibility to the whole grid. Then things get worked up, and so that's something we try to avoid when obviously we try to avoid that you have multiple levels of redundancy to prevent that from happening.
Got it. Okay. Thank you.
Yeah.
So Carl Reinhardt, back for a reprise. Your third or fourth slide was a timeline. Can you go to that slide? And the question I'm going to ask is going to be associated with.
Now, which one was that?
You had a timeline slide.
Oh, okay. Yeah. There it is.
And so what I'd ask is for some context in terms of the industry, because I know that you're also the chairman of the subcommittee for the utilities.
Yeah, Smart Networks Council, yeah.
Yes, and so that was formed in the 2007 or so time frame. And I had never heard of that before I was kind of preparing for your presentation. Could you describe the importance of that organization and how it fits into the broader picture? And
yeah. So UTC, Utility Telecom Council, which is an organization made up mostly of utilities and vendors that sell into the utility market, and they take up they were kind of our lobbying arm into DC for telecommunications needs for utilities, you know, and so that's really their function in life. And so we work with them a lot on the spectrum issue and policy issues around you know, where telecommunications are going with the federal government. But they formed a Smart Networks Council, which is made up of numerous IOU utilities, well, any utility member that is part of UTC. And there we discuss, you know, what does smart grid communications look like? What does architecture look like? You know, what are our needs? And, you know, pretty much everything I put in here has been a topic of discussion within that framework. And this group then tries to either you know, write papers or do research on it, or you know, get some consensus opinion around around those needs. I mean, one of the things they recently did was a study on the RF effects, the health effects. Now, we're not really a health organization, but we did do a lot of research on the health effects of the RF in the meter and that sort of thing. So it's a you know, it's a fairly large group of people that talk about these issues.
And so there are other lobbying organizations like the IEEE that, you know, has broad interests such as that. But there is a need, I gather, a gap that the UTC fills that other
Yes.
organizations.
Yes, absolutely. Yeah, absolutely.
So let me ask you a question. I should say, I mean, I guess this part wasn't a surprise to me how much you embraced IP, but I do have to say, back when TCIP formed around 2004 and we brought utilities together, we'd talk about TCP IP and standard communications. And my gosh, everyone shuddered. And so this is a changed world.
Well, you know, and I know exactly what you're talking about, because there is a native reluctance of you know, some of these power guys to even think about IP, and that's not all gone either. No. There's still a lot of that out there, and I've seen that myself. But I think that, you know, what the future is IP, and to say that it's not, or say that staying with the status quo is an acceptable approach, to me just is not forward-looking, and is, you know, pretty much putting your head in the sand, because I think IP is going to be able to deliver capabilities beyond what they're thinking of today. Again, you know, when we design these applications today, we're doing it with blinders on, because this is the way we've always done it, and this is all we need this thing to do is perform this function, and not looking at it like, well, once it's out there, what other functions is it going to be able to perform? And wouldn't it be neat if it could do this, or wouldn't it be neat if it could do that? And those other protocols just aren't going to support that kind of capability.
So if I can jump in again, if then I listen more to your presentation and I see a real emphasis on wireless communications, and again, that's something that we talked about very early on. Clara Narstedt, my colleague here, is the lead of a push. And the question that she might be waiting in line to ask, but I jumped her to it, is, yeah, so what about wireless communications for control? Not just sensing, not just monitoring, but real control. Where's the industry on that, and where are you on that?
I think the industry is, it depends on the kind of control. And if you're talking about relay protection, maybe not so much yet. You know, yet. And the reason I say that is this kind of stuff has to be out there, and you have to get a comfort level with it, that yes, it is performing, yes, it is reliable, or not. You know, if it's not, then okay, you know, call a spade. But if it performs, as you deploy these new technologies, and a lot of this stuff hasn't been deployed before in this kind of framework. You know, like WiMAX is fairly new. I'm not saying it's brand new, but it's fairly new to be deploying that in a SCADA control environment, and we're going to do control over it. We are. Now, again, not relay protection control, but you know, grid automation control functions will definitely be operating over that. So I think there, you know, again, it's going to be getting the folks that are, you know, that aren't used to this to see it actually work. I mean, you know, another interesting notion is some companies are doing that relay protection over MPLS. And that's exotic. You know, I think. I mean, that's really out there. Altalink up in Canada has done that with the Alcatel-Lucent product, And for me to go suggest to our power system engineers, let's do relay protection over MPLS, that's just the days, we're not ready for that yet. Someday we will be, but right now we're not. Yes, sir.
Yes, I got a question with, first, I understand that traditionally right now, most of the SCADA procedures still relies on the centralized control room for the power flow analysis, such as state estimation, contingency analysis, and remedy action scheme. So I was wondering how the smart grid communication that you're talking about in this presentation can reshape those SCADA procedures in the future.
Yeah, that's another interesting one. Yeah. I think you're going to see a much larger movement to distributed intelligence being pushed out into the substation and away from centralized. And some of the discussions we had the past couple of days is having more of the intelligence making the decisions around what to do, because if the application is smart enough, it'll be able to make those decisions a lot faster, and thus, improve stability or eliminate an instability situation much faster than an individual can react to it. So I think you're going to have to push that intelligence into the substation to enable that. So I think that's going to be the direction that things should go. But I think there's more time to more development time needs to be done to get us there.
I've tried not to hog the time. Carl Reinhardt again. Hey, on a different subject, you've got a reference to 7628, and they talk about the logical interfaces as a way of visualizing the grid. Is that structure that they use, is that useful to you as a guy building the architecture?
Yes, it is to an extent. It's a spaghetti diagram, and so it's very complicated, and so I think it is representative of what those interfaces are. One of the things that we're doing in the Smart Networks Council that we're talking about is looking at an architectural framework with those interfaces in a much more condensed version that is perhaps at a higher level. We have analyzed our security posture to 7628. And we have a document that demonstrates how we map to the controls specified in 7628. But it's from a logical interface perspective, I think it's helpful, but we don't look at it every day. No.
Okay,
Right.
Thank you again, Doug. Before we close, let me announce that our next seminar is the first Friday of the month of May, which would be 3 May. 3rd of May, we have Ron Melton from the Pacific Northwest National Lab talking about the Pacific Northwest Smart Grid demonstration, and we hope to see you all for that on Friday, May the 3rd. Thank you.